Hi guys, let me see if I can help you with this problem that we didn't have a chance to do in class today. Problem 9.33 on page 289. This problem deals with moment of inertia. In this problem we have four equal masses of 0.2 kilograms distributed like this as in the sides of a square. And they are connected by very thin rods that we can ignore the mass of. So it's pretty much 4 point sources separated by a distance of 0.4 meters each one. And what we'll do is we'll compute the moment of inertia of this mass distribution with respect to different axes of rotation. On A, we will compute the distribution with respect to the axis of rotation that goes right here through this O. So if you would imagine all of these masses turning around this center, either counterclockwise or clockwise around this axis, we'll compute the moment of inertia this way. Then on B, we'll compute the moment of inertia with respect to the axis AB. So if the distribution of masses would go like this. And on C, we'll compute the moment of inertia with respect to the axis CD, which will be going like this, all right? And then we'll compare and we'll see whether it's harder to put this mass distribution to rotate this way, or that way, because you remember that the moment of inertia tells you something about how hard it is to put something, to make something rotate. It's very much related to the mass. All right, so to start, let's recall the definition of moment of inertia. Moment of inertia is the sum of the product of the mass times the distance square from the axis of rotation. So in this case, we have four masses that are at a certain distance. All of the masses in this case are at the same distance from O. And if we just use a little bit of trigonometry here, we'll use this green triangle right there. So the side of the square is 0.4, so this is 0.2 here, this here is 0.2, and if you use Pythagorean theorem, you get that the hypotenuse there is 0.28 meters, all right? And all of the masses will be at the same distance, 0.28 meters from O. Therefore, I can say that the moment of inertia of one particle is the mass times the distance, 0.28. Actually, why don't I just put the mass already? So it's 0.2 kilograms times the distance, 0.28 meters squared. This is the moment of inertia of one of those masses. There are four that are the same distance, the same mass. So what I'll say is that the total is all of this multiplied by 4 for the four masses. If you do the math, where are my notes? Hold on, I did do the math this time. So the moment of inertia then is when you multiply all of this, you will get 0.064 kilograms times meter square. The 4 is because of the four masses, all right? Okay, now let me change colors and do purple. And we're going to compute the same thing, but now thinking about the AB axis. So with respect to the AB axis, notice that all of the masses are at a distance of 0.2 meters here, all right? So I will be 4 times, because all of the masses are equal, the distances are equal, so 4 times 0.2 kilograms. Each one of those is at 0.2 meters square away. So the moment of inertia, if you plug this into your calculator, you get 0.032 kilograms meters square. All right, and then let's do the last one, C. So C is kind of cool because these two masses masses here, this one and this one, are at a distance 0.28 from this axis, right? But these other two masses are right on top of it, so the distance is 0 in that case, okay? These two are at 0.28, this and that, but those two at a distance 0. Well, if the moment of inertia is defined as the product of the mass times the distance, and if the distance is 0, there's no contribution to the moment of inertia coming from these two masses that are right along the axis. Therefore, the moment of inertia in this case is simply 2 times, because of those two masses, times the masses, 2.2 kilograms, times the 0.28 meters squared. And if you do it again, you will get that this is equal to 0.032 kilograms meter squared. Alright, so if you take the big picture now and compare what we've computed, we have found that we would need the same amount of kinetic energy, we would need the same effort to put this mass distribution to rotate this way or this way, because the moment of inertia is the same, 0.032 and 0.032, and we would need more energy, we need more effort to put this mass distribution to rotate this way, clockwise, counterclockwise or clockwise. Alright? So that's all there is to this one. I hope it's clear.